This is the solution to the first three midterms. Before we begin, let's recap on a few basic concepts. In three-phase systems, personally, I always convert deltas to y's. That is a thing I do. And then I work only on the phase A of the three-phase system, the single-phase equivalent of the circuit. That's what it's called, right? So we're going to need a few formulas. Well, the formulas that I use most often, not the only ones, of course, but the ones that I use the most. In a balanced delta, that is a delta in which every branch of the triangle has exactly the same impedance, like this one. To convert that to a y, I merely divide the impedance by 3. 3 plus j 9 ohms, 1 plus j 3 ohms. As simple as that. What if the delta is not one of impedances like this one? Well, in a symmetrical delta of sources, that means if all the sources have the same RMS value and are out of phase by 120 degrees, to convert that delta to a y, I only focus on the source between phases A and B. That is the only one I will use to transform the delta into a y. That is the value of that one, 173 RMS volts with 90 degrees. Well, to find the corresponding y for the phase A, I divide the RMS values by √3 and I subtract from the phase 30 degrees. That's how I find the phase A y equivalent source. 100 volts with 60 degrees. Now we know how to convert deltas of impedances and deltas of sources to equivalent y's. What other formulas do I use? Well, the ones for power. You see, to compute single-phase power, I mainly use 3 formulas. And if I am solving the single-phase equivalent of a three-phase system, I have to remember to multiply that times 3, because after all, the single-phase equivalent is only 1/3 of the power system. Well, let's begin. 3 different cases. If I know if the voltage and the current are an impedance, we can draw it like that, assuming that the impedance is absorbing power, like this, the impedance is delivering power. But the power is computed using the Steinmetz formula. Complex power is the voltage multiplied by the conjugate of the current. The real part is P, the active power or average power, and the imaginary part is Q, the reactive power. Let's do that with numbers now. For that, let's say that we know the voltage is 120 volts RMS, 30 degrees, and the current is 12 amps RMS, negative 10 degrees. Compute the power that is being absorbed by the impedance on the left or delivered by the impedance on the right. Use Steinmetz formula. V times I conjugate. That is the voltage 120, 30 degrees multiplied by the conjugate of the current, 12 amps, positive 10 degrees. Multiply them, and that gives us that the active power or average power absorbed by that load is 1.1 kilowatts, and the reactive power absorbed by that load is 0.9 kilovars. Well, of course, I'm assuming I'm computing the one on the left absorbing power. If I'm using the one on the right, then those would be delivered powers. A second case. If what we know is the impedance and the current through that impedance, then what I do is I compute the power multiplying the impedance by the square of the RMS value of the current. That is impedance, that is the current. I know them both. I compute the absorbed P and Q with that formula. Impedance Z, a complex number, multiplied by a real number, the square of the RMS value of the current. That gives us the real part and the imaginary part, P and Q, the active power and the reactive power. With numbers, sure. Let's say the impedance is 3 plus j 4 ohms and the current has an RMS value of 7 amps and the phase of 37 degrees, which is the formula, this one. Z, 3 plus j 4, and the RMS value of that current is 7. Squared is 49. Multiply that and we get that impedance is absorbing 147 watts. That is P, the active power, the average power. And it's absorbing also 196 vars, the reactive power. The third case. In this case, what we have is the impedance and the voltage across the impedance. We don't know the current. What we have is only those two values. In that case, we use that formula on the right. The RMS volts squared divided not by the impedance, but by the conjugate of the impedance. That gives us again P and Q, right? Let's do that with numbers, right? Let's say that the impedance is again 3 plus J 4 ohms. By this time we know the voltage, and the voltage is 23 RMS volts with a phase of 137 degrees. The formula, RMS squared, that is 23 squared, divided by the conjugate of the impedance. You see 23 squared divided by 3 minus J 4 ohms. And that gives us the complex power absorbed by that impedance, 63.5 watts and 84.6 VARs. Let's go and turn our attention to the midterm number 1. Question 1. The combination of inductors and capacitors in figure 1. Which figure? This one. Between nodes P at the top and Q at the bottom operates connected to a non-shown AC system with a frequency of 100 Hertz. We are told that all that group can be represented, simplified, if you will, to a single element between nodes P at the top and Q at the bottom. The capacitance values are 100 microfarads, all of them, and both inductors are 50 millihenries inductors. The question is, find the element. Find the simplified inductor or the simplified capacitor, either in henries if it's an inductor or in farads if it's a capacitor, right? B. What would be the effect on your answer to part A above if the horizontal capacitor, that one, was doubled in value? Let's proceed. That exercise can be solved in many different ways. For instance, you can find the impedances of each one of those reactive elements, every capacitor, every inductor, convert the top triangle into a Y, simplify a capacitor and an inductor in series on both sides, put them in parallel, put that in series with the capacitor on the top, and that would be the simplified element. You can do something equivalent. You can simplify and convert the lower triangle into a Y, etc. But I'm not going to do any of that. I noticed right away that nodes X and Y out of symmetry have exactly the same voltage. That means that the current through that horizontal capacitor is going to be voltage at the origin, Vx, minus voltage at the destination, Vy. Same values, zero voltage drop, zero current. There is no current through that capacitor. That capacitor is doing nothing in that circuit. So we can eliminate it. So you see, it was a red herring there. Now we convert those reactors to impedances and put them in series and then in parallel and be done with that. Let's do that. Omega is 2 pi 100 628 radians per second, right? So the impedance of the inductors is J omega L, J 31 ohms. The impedance of the capacitors, negative J 1 over omega C, negative 16 ohms. Put each capacitor's impedance in series with the inductor's impedance, and then in each one of the two branches we have an impedance that is in reality J31 minus 16 ohms, and put them in parallel. That's what we do. That is J7.75 ohms. What kind of an impedance is that? An inductive one. So we have an inductor as the equivalent element between nodes P and Q. To find the value of the inductance, divide that reactance by omega, right? 775 ohms divided by omega, that is 12.3 millihenries, and that takes care of that part. The other part B, is what if we change the value of the horizontal capacitor to twice as big in capacitance? Well, we already have an answer for that. There is not going to be any current through that capacitor, so it does not matter the value of that capacitor. It doesn't even matter if we connect there anything, a shoe, and still the impedance is going to be just the impedance of a 12.3 millihenries inductor. Now the second question of midterm 1. if the parallel circuit on the right, you see RP in parallel with JXP, is equivalent to the series circuit on the left at a given frequency, RS, JXS, find the RP and XP as functions of RS and XS. That is a classic, right? Well, the inverse, that is the admittance, the inverse of the impedance of the series circuit, the admittance of that one, has to be equal to the admittance of the circuit on the right, the parallel one. But the admittance of the parallel one is just the sum of the admittance of the resistor, 1 over Rp, plus the subseptance of the reactor, negative J1 over Xp. We simplify that, and we find out, simplifying that a little bit, that the expression on the top, I have multiplied numerator and denominator by the complex conjugate of the denominator. That converts the denominator to a real number, and then we find the real part and the imaginary part of the left-hand side, and we equate the real part of the left-hand side has to be equal to 1 over Rp. The imaginary part of the right-hand side has to be equal to 1 over Xp. And then we say, oh, real part of the left has to be 1 over Rp. Real part, imaginary part, sorry, of the left has to be equal to 1 over Xp. Find the inverses of those, pam, and voila, we have Rp and Xp as functions of Rs and XS. And that was that second question. Now, question number 3 of the first mini midterm. The oscillogram shows the current and voltage in a series combination of two elements, a resistor and a reactive element. That is, the other one could be a capacitor or an inductor. They're not telling us. They're not telling us that. The peak-to-peak value of the voltage Y sub 1 is 15 volts. The peak-to-peak value of the current Y sub 2 is 3 amps. What is the value of the resistor in ohms? That is the first part of the question. And the second, what is the value of the reactive element, either in henries, and there is a typo there, it should be henries, or in farads if it's a capacitor? Well, let's see. The peak-to-peak value of the voltage is 15. The amplitude of the voltage is 15 over half. The RMS value of that will be the amplitude divided by root 2. That's right. So the voltage is a phasor that has an RMS value of 15 over 2, the peak value divided by root 2. And what phase? Well, the voltage is the phase reference. So by definition and convention, its phase is 0 degrees. That is the voltage phasor. 5.3 volts, 0 degrees. It's a real number. What about the current phasor? Well, the current phasor has a peak-to-peak value of 3 amps. Fine. Divide that by 2, divide that by root 2, that is the RMS value. But what is the phase? Well, observe in the curve that the current is lagging behind the voltage by 2 milliseconds. Convert those 2 milliseconds to degrees. How? Well, we notice that the period is 10 milliseconds, so 10 milliseconds are equivalent to 360 degrees. You do the proportionality. If 10 milliseconds is 360 degrees, 2 milliseconds will be 72 degrees, of course. So the current phasor is 1.06 amps RMS with a phase of negative 72 degrees. We divide V by I and we get Z, the impedance. Real part, the resistor, 1.55 ohms, and the reactor is an inductance. Well, because the frequency is the inverse of the period, 1 over 10 milliseconds, that is 100 hertz, we have omega, which is 628 radians per second. We divide the reactance, 476, by that omega, and we find the inductor's value is 7.6 millihenries. And that was that. Now, midterm 2, that is the first question of the mixed midterm 2-3. A three-phase symmetrical Y connected voltage source. Wow, that's quite a mouthful, right? A three-phase symmetrical Y connected voltage source. So it's a voltage source that is symmetrical, it's three-phase, and it's connected in a Y connection. That source is feeding a delta connected load, this one, and the Y connected load, the one on the right, through non-ideal wires as per the figure. Compute the total active power and reactive power, A, for the source, B, for the delta load, and C, for the Y connected load. Let's proceed. Let's magnify the circuit to better work on that. The system is balanced. That means that the impedances on each one of the branches of the deltas, of the Ys, and the lines are exactly the same in value. Well, the first thing is convert that delta to a Y. Divide that impedance, 2 plus J3, divide all of that by 3, like that. 2/3 plus J1. And that is the first thing I do. Convert everybody to a Y. Secondly, out of symmetry, the voltage here, there, and there, that is the voltages at the centers of all the Ys, are the same. Electrically, they are at the same point. So that's why I can solve only this part of the circuit, separate it from the rest, a single phase equivalent. And that is what I am about to do. Solve that circuit. Well, the first part is find the power and the source. How to do that? Well, this is the way I'm going to do it. I will find the equivalent impedance seen by the source and then divide the RMS volts of the source by the conjugate of that equivalent impedance. And that is the power supplied by the source. Of course, I get to multiply that times 3. This is only 1/3 of my three-phase circuit. Let's do that. Keep in mind that this circuit represents only 1/3 of our power system. If we compute the total equivalent impedance seen by the source this way, check this out. These 3 plus J5 in series with 2/3 plus J in parallel with all of this branch over here. J7 in series with 3 minus J5. We do all of that, and that is the equivalent impedance seen by the source. 3.58 ohms plus J5071 ohms. And now that we have that, we can divide 100 volts squared by the conjugate of 358 plus J571. And that is the power, 1/3 of the total three-phase power of the source. Let's do that. 100 squared, the RMS volts squared, divided by the conjugate of the impedance. What is missing there? Times 3, right? To account for the power in the other two phases. We do the math and we say that source is delivering. You say, how do you know that? What you computed is the power absorbed by all the loads and all the lines and all that. Well, we have Telegen's theorem that says that the source, being the only one, has to be providing all of that absorbed power. So that is the power delivered by the source, 2.4 kilowatts and 3.8 kilovars. And that is that. No, that is only part A of the question. Power delivered by the source. Now we get to compute the power absorbed by each one of the three-phase loads. Well, this is what I'm going to do. I will compute Vx, the voltage at that node X. Why? To do exactly the same again. I find Vx RMS squared divided by the conjugate of that impedance, 2/3 plus J. So I found the conjugate divide. And that I multiply times 3 to get the power in the delta. This way. Let me write down here what is the equivalent impedance seen by the source. I want to use that power formula in the delta. 3 times the voltage at that node, the RMS, Vx RMS squared divided by the conjugate of that impedance, 2/3 plus J. That is the conjugate 2/3 minus J. Fine. To find Vx, what I'm going to do is compute the current in the source and compute the voltage drop in that 3 plus J5 ohms and subtract that voltage drop from the value of the source. Determine the current in the source. Oh, fine. The voltage in the source divided by the equivalent impedance seen by the source. That is 15 amps with negative 33 degrees. And then I can compute the voltage Vx as the voltage of the source minus the drop in 3 plus J5, and that is 13.6 volts with 17.8 degrees. That is the voltage Vx. And then we can compute the power in the delta load this way, 3 times the RMS of Vx. That is 1358 square, divided by the conjugate of one branch multiplied times 3. The delta is absorbing 255 watts and 383 vars. Let's go now for the Y. Well, we could do the same. We can compute I sub L, the current here, now that we have Ex, divide that by that impedance of that branch, and then the drop in J7, compute the voltage across the... Wait a minute, you say, I don't need to do all of that. I can compute the current IL, and then use the Z RMS of IL squared and find the power directly if I multiply that times 3, right? Yeah, IL is Vx divided by that impedance, and then I use that formula. The power in the Y connected load is 3 times Z, 3 minus J5, times the square of the RMS amps. That is the square of 377. That is the power absorbed by the Y load, 128 watts and 213 vars negative. So that load is producing reactive power, but we knew that it's a capacitive load. And that takes care of that question 1 of the midterm 2-3. That was the second midterm. Let's go now for the third midterm. That is the second question of midterm 2-3. A second order circuit. The switch has been in position A for a very long time. At t equals 0, the switch swings from position A to position B. First, part A. What is the initial value of the current in the inductor? B. What is the initial value at 0 plus of the time derivative of the capacitor of voltage? That is dVc dt at 0 plus. What is that? And C. After the switch operates, that is for t after 0, compute the eigenvalues and say whether the circuit is overdamped, underdamped, or critically damped. Let's do it. We do the usual in second order circuits. Snapshot at 0 minus. From that snapshot, we obtain the initial value of the current in the inductor. We obtain the initial value of the voltage in the capacitor. In this case, it's 0. That is not even part of the snapshot. And then we take a snapshot at 0 plus, and in that snapshot, inductors behave like current sources with the value IL0. Capacitors behave like voltage sources with the value VC0. We have seen all of this. This is a recap. And then we obtain the other two parameters. We obtain the voltage in inductors, VL0, and the current in capacitors, IC0. And with them we compute the derivatives. The voltage in the capacitor is changing at that instant in time at a rate IC0 divided by C, and the current in the inductor is changing at a rate VL0 divided by L. That is the usual. Now let's do that usual stuff here. First, the circuit, right? The snapshot at 0 minus, that is one. The right-hand side of the circuit is not even there. The circuit is in DC steady state, so the inductor behaves as a wire. And we compute the current in the inductor is going to be 10/25 amps. The voltage in the capacitor, it is not even connected. And because the problem does not give us the value of the charge in the capacitor, it's fairly safe to assume the capacitor is discharged. VC0 is 0 volts. Now the next step, what was that? Oh, snapshot at 0 plus. In there, the inductor, this one is represented by current source with the initial value of its current 5 amps. And the capacitor is represented by a V source of 0 volts. That is, in this case, by a wire. This wire, that is the capacitor, right? 0 volt source. Yeah, not to waste a good source, we use a wire. In there, I'm going to compute IC0, the current in the capacitor at 0 plus. Why? Because that is the only value I really need. Well, that value is just negative 5 amps, right? Yeah, absolutely. There is no current in the right-hand side 2 ohm resistor, so that means that all the current in the source is flowing through the capacitor, but backwards, negative 5 amps. With a negative 5 amps, I divide that by the capacitance, 10 micros, and I get the voltage rate of change in the capacitor. 500,000 volts per second. Yes, and that instant in time, the voltage in the capacitor is 0 volts, but it's decreasing at a rate of 500,000 volts per second. Super. We're done with that. Let's find the eigenvalues. Well, let's represent that circuit at t after 0, and let's use Heaviside P operator. You may be thinking, why don't I use the Laplace transform? Well, the thing is, those are conceptually different things. You see, using the P operator, we are analyzing the circuit in the time domain in our universe. When we use the Laplace transformation, we are transferring the circuit to the frequency domain, to another universe to solve that circuit there. I don't want that. I want to solve my circuit in the time domain. I use a P operator. So I replace reactors by P operator impedances. That, by the way, they have the same shape as phasor impedances. They have the same shape as Laplace impedances, but P instead of S. So it's no big deal. There. That is our Heaviside P operator equivalent circuit at t after 0. The left-hand side of the circuit is gone. It's not connected. It's not part of the circuit anymore. So we have there the inductor, 0.05 P, the capacitor, 10 to the 5 divided by P, and the 2 ohm resistors. Wait a minute. Who is that current source F? It's a fake current source with a value of 0. I need that so that I can actually use my calculator to solve for the differential equation. Otherwise, I'm going to get 0 equals 0 in my solution. You try it or watch the video on using fake sources to find the differential equation that we saw in 251, EECE 251. Okay, let's write that one KCL equation for that circuit. Current going in, the fake current source F. We're not making that 0 yet, all right? So we can write that equation. And that is equal to the 3 branch currents, the one on the left, the one through the capacitor, and the one on the right. Solve for V1, how? Well, through the calculator, of course, through the HP50G. We find that, which is nothing else but the differential equation, whose solution is V1, the voltage there at the node 1. Now it's the time to make F0. So the numerator becomes 0. And we have a second-order differential equation with coefficients 1, 50,000, and 4 millions. From that characteristic equation, we find the eigenvalues. Negative 80 seconds inverse and negative 50 seconds inverses. Because the two eigenvalues are real and are different, the system is an overdamped circuit. We can say that with aplomb. The circuit is overdamped. And we're done with that. Now, let's see an even more interesting exercise, more than that one. You say, no, wait a minute. What exercise is that? This one. That one. Source on the left, 2 ohms, 2 ohms, 2 ohms, 50 millihenries, 10 microfarads, a switch that is in A and swings to B at t equals 0. Yes, that's right. The switch has been in position A for a long time. At t equals 0, the switch swings from A to B. That sounds familiar. Yes, it does. What is the initial value of the current in the inductor? Well, What is the initial? Wait a second. This is exactly the same previous problem, the one in the midterm, in the third midterm. Not quite. This is a more interesting one. Why? Because the source is a sinusoidal function of time. 14.1 is the amplitude of that source. 140 is the angular frequency in radians per second, and the phase of 25 degrees. I'm using the convention used by physicists and engineers, so I'm adding apples with oranges. Radians 140t and degrees 25 degrees, but it's fine. So that is the convention. Let's proceed. How do we go about that? Well, most of the exercise will be the same. The only thing that changes is how we analyze the circuit in the snapshot at 0 minus. That is all. Snapshot at t equals 0 minus. At 0 minus, because the switch has been like that for such a long time, the circuit is in steady state. Because the source is a sinusoidal one, the circuit is in AC steady state. That means we can use phasors and impedances to analyze that circuit. And that is exactly what I am about to do. The angular frequency is 140 radians per second, right? Cool. So we can represent the inductance as J omega L, J 7 ohms. The voltage source with a phasor. 14.1 is the peak value. 10 volts is the RMS value, and the phase is 25 degrees. In that circuit, we can compute the phasor for the current in the inductor. This one. 137 amps with negative 49 degrees. But I am not there yet. That is a representation of the sinusoidal function of time. That is the current in the inductor. The current in the inductor before you move that switch out of A is 137 root 2, that is a big value, sine of 140t minus 49 degrees. Amps is the function of time. We want the initial value of that current in the inductor, that is right at 0 minus. Just make t equals 0. That is all. And you will have the initial value of the current in the inductor, negative 1.47 amps. The rest of the circuit is exactly the same as before. The only thing that changes is analyzing to find the initial value of the current in the inductor. And this one is an even more interesting one that I'm leaving to you viewers as an exercise. Why is it more interesting? I shall tell you in a moment. You say the switch has been closed for a very long time, and at t equals 0, the switch opens. The questions are the same. Well, how is that different? Well, what is different is that now at the snapshot at t equals 0 minus, the capacitor is also there. Please proceed. You know how to do that. And with that, we've finished this little video on the solution of midterms 1, 2, and 3 as part of your getting ready for the final exam. Thank you very much and good luck in your coming final exam.